recording. So what I'm gonna do is, like I said, I'm gonna go every question. I'm gonna kind of look at it, read it out loud, give everyone kind of like a while to think about it, and then like kind of I'll kind of say I think it's probably this, and then we can kind of see together if people agree or if they think there's a flaw somewhere and what they think, and then together we'll come to an answer, and that's kind of the back and forth is kind of where we learn. Okay.
I think that's a good idea.
Oh, and something funny to do. Let me just. Yeah, fuck off. Give me my timer. There we go. Maybe really quick fuck with the controls a bit. Yeah, okay. So, right. Jesus. It's always scary when all the questions are so short.
Yeah.
Right. Name 3 main components. Okay. So name 3 main components in a parallel computer system and describe them. Yeah. So, yeah, personally, for the 3 main components, what I would do is I would say there's a node, which is the thing that does the computing.
It's like the architecture, right? Like sort of what we.
Yeah. So that's I think I am like kind of seeing this question in the way of the architecture. Yeah. So
Yeah.
I think you have a node, which is the thing that does the computation. I think you have the switches. I like the terminology here is going to be wrong for on my part, but the switches
Like the
allows.
is the nodes the same as cores?
Hmm?
Like
Yeah,
the, for
well,
example,
sort
amount.
of. So nodes, say you're talking about Delft Blue. Delft Blue
Yeah.
has many nodes, and each node has 24 cores. So
Yeah.
each node
Okay.
is like a small computer, and it needs to talk to other computers. And
Mm.
in one computer, every node is a core. In supercomputers, the nodes are like more cores. Because it's like a computer on its own. Allows the nodes or manages the communication. Can't type between nodes over links so that not every node has to be connected to each other. Directly linked. And a link medium to get transfer data between nodes and switches. So this would be my answer probably. Or that part of the system that does the computation, the part of the system that and the medium which transfers data. So, do you all agree with this, or do you think that would you answer differently?
I think this is one part, or this is one part, right? Like just you're now discussing the, in a way, the architecture.
Yeah. So it's saying that
Yeah.
name 3 main components in a parallel computer system. So technically, if there could be more components.
Yeah.
Yeah.
But should we not? I'm just trying to think about how the lecture slides are sort of organized, because it talks about the architecture, then it talks about like the memory, how the memory is used. Does, like, if it's shared or distributed, would that be a part of it as well?
So I feel like another way that you could interpret this question is go. You have memory, you have cores, and then some other third thing. I don't know. But I feel like that
Network.
might be another way to interpret this question.
Yeah.
Um,
I have a feeling, like, I'm just gonna have a little look, because I feel this question is somewhere either in the quiz or in the other exam. So I'll just have and I think it's a very similar question. Does it help if I look it up?
Yeah, what
just
we'll do
about.
is for now we'll just do it by heart, and then like at the end we can look it up as it sounds.
Yeah. Okay.
Okay. So what are the main?
Wouldn't you say like, sorry, wouldn't you say something like a kernel processor or a like whatever distributes the threads to the different processors is a big component of a parallel computing system?
Something which distributes the task.
Sorry?
Well, the thing
Yeah.
that distributes the tasks is still a CPU, or it's one core. One core is the one that is the thing that like distributes it to the rest. They'll just be the master or something. Or I guess
Mhm.
I don't know if CPUs have their own core
I'm,
thread
I'm
scheduler
looking at my
nodes.
what I wrote down about I think this was even the first lecture about parallel computing and the main. And there's different types like end-to-end mapping, one-to-one mapping, etc. But all of them have a bunch of processes, a kernel thread that distributes the threads, and the processors themselves, which is how the three components he has in every different type of parallel computing mapping
Yeah, but
described.
yeah, but this is about a parallel computer system. So I feel like this is more about
Yeah.
like the physical system than the logical.
Okay, fair.
I feel like your answer like might give you points as well. Because it's like it's a very vague question, so I think they'll accept many
Yeah.
answers.
Yeah.
So I think there's multiple ways you can like interpret this. So yeah, we can look at the end to see if that one would give you points as well. What are the main properties of a static interconnect network? Oh god.
So the main properties.
Yeah, or performance metrics, it says.
Okay, so is that the thing that's I have to look at the slides.
I feel like a static interconnection network is one that doesn't have any switches.
No, exactly, no. And because the switches is the dynamic network.
Yeah. So no switches, computer or nodes communicate directly, which means many links.
Oh, I got in my notes fixed topology for static networks.
Yeah, yeah, that makes sense because it doesn't like swap. Yeah, fixed
Yeah.
topology. So the layout doesn't change. You can always go, hey, I'm talking to this thing. That is that PC.
But I do have in my drawing for static networks, I do have also a switch in it. It just doesn't, I guess, switch dynamically. It's just maybe one pathway or something
Uh,
for this.
yeah. So it says that the area and rings would be static. So I guess the nodes are the switches almost.
Yeah.
Yeah. So it's not like there's no switches. It's like the more that the nodes are the switches.
And then it has this thing about the diameter, which is the
Yeah, there's a diameter, the degree, the edge connectivity, the
yeah
bisection bandwidth, and the cost.
bisection bandwidth. Yeah.
Yeah. Yeah, static interconnection network. Yeah, so right now I've got no switches, but it's more like nodes act as switches. Oh, goodbye, Tim.
Yeah. Formed by links, connect different nodes. Fixed topology.
So I'd be wrong because I was thinking of a different thing. Yes, it asks what are the main properties or performance networks.
I think the performance has to do then maybe with the bisection bandwidth and the diameter and stuff like that, and maybe also the cost.
Yeah, so we would have the performance metrics would be, and this is shamelessly copied from the slides, degree, maximum direct neighbors, diameter, longest distance between two nodes, if I'm correct.
Yeah.
It is edge connectivity. What's that one? Minimum number. Okay, so how many edges have to be removed to split the network in two? Edges to be removed to split
I
network.
thought it's a bit vague for me, the edge connectivity. Like, so the amount of edges that need to be removed.
Yeah. So for example, in the linear array and rings at the, in my screen on the top right, if you
Yeah.
if you remove one edge, it's just two parts.
Yeah.
But on here you have to remove two edges because you can remove one edge and then it'll become
Okay, yeah.
a linear. So and here you'd have to remove four edges because if you remove
Yeah,
one,
yeah.
it has a longer trip.
Yeah.
Bisection bandwidth is edge connectivity, but two parts.
Yeah, how much?
Bisection bandwidth. Yeah, it's the same, but then like the parts need to be equal, right?
Yeah. Like you cut it in half.
Have to be equal. And cost, yeah, total number of wires, but like that's not. It can be done in many ways.
Yeah.
Communicate through other nodes. Fixed topology. Right. So I wouldn't have like half this answer, but you know, fuck it. Main difference between store and forward and cut through routing. I have never heard these terms before. But what I do think the main differences would be that store and forward caches the data, while cut through doesn't, because just from the names, cut through sounds like it's just, okay, forward this message, you cut through me, I'm almost not there. And store and forward is just, hey, I'm storing this message, make a new request, and I'll cache the data myself as well.
You could be right. I have no idea. I've actually never. This
No,
doesn't ring.
I don't think this is from this. This is from like this is not in this year. I think.
Probably because those terms are completely new for me.
Yes, store and forward does caching, cut through does not. This means that cut through is faster. Okay, fuck it. Random answer. Am I right? No idea. Describe the meaning of simd, mimd, spumd.
That's just like that's in the
It's in the slides. I'm just trying to remember because I know the differences. I'm just trying to remember the fucking what they're short for.
Yeah, I got it. I got my book here, so it's
Single
in the book.
instruction, multiple data, multiple
Yeah.
instruction, multiple data, but SPMD, I don't know, single something, multiple data. I would guess. It's single or multiple instruction, and then single or multiple data usually. But SPMD, I never saw this.
No,
It's not in the book.
Data. One instruction is performed on multiple multiple bits of data, like array, not indices, parts of an array, multiple instruction, multiple data. Each bit of branch independently. So for single instruction, multiple data, I said one instruction is performed on multiple bits of data. For multiple instruction, multiple data, each bit of data can perform instructions and branch independently. Although the word bit is wrong here, I'm using bit not as like 1 or 0, but as like chunk. So I'd rather change it to chunk. Each chunk of data can perform, or each chunk of data gets a thread which can perform instructions and branch independently. Instruction. Yeah, and then I feel like the SPMD is something like shared process, multiple data, but I'm not entirely sure. I think this was in thing 1, so I didn't bother looking it up. Let me have a look. Lecture 1, slides. Let's just real quick see. Yeah, a final report. Okay.
Which one
Yeah,
are you looking at?
50% lab. Okay, so LabWord is open MP and MPI assignments. Good to know. And I was looking at the. Yeah, so this is MIMD, UMA, NUMA. Is it even in here?
There.
No, it's not. It's not even in here.
Oh, but it's not really explained.
No, but the term is not even used. Oh well, whatever. We don't know.
Maybe he dropped SPMD for us.
Yeah, probably. Okay, so 5.
But it's not even mentioned in the book, so weird. But,
5
Yeah.
is Amdahl's law. I know that one. So that is their if a program a program can only be parallelized up to the part of it that is sequential.
There's a fraction or something,
Yeah.
right?
So
Yeah.
if P% of a program can be parallel or can be executed in parallel.
Yeah.
In parallel, the max speed up is, and now I need to do some math in my head, so the time is P times A plus 1 minus P times B. And that's times, yeah, and this is like the, so as B goes to 0, so that's the parallel time, and the normal time would just be A plus B. What's the fucking, I remember it being something simple, like 1 over P, like the max time it takes is 1 over P. But
I'm trying to find it at the moment.
like I know what it is
It
in.
gives an upper bound in a way for like at some point the amount like doesn't matter how many more processors you're gonna throw at it, like it will speed up will just stay the same.
Yeah. So the way I remember it is if P% of a program can be executed in parallel, or let me rephrase it, has to be executed in sequence, the maximum or the minimum execution time is
Something like
well, it's not P itself, but
it was something that if you take it to
the limit of
limit.
P goes to or n goes to infinity. So yeah, the exact wording the exact wording is about a speed up, not a flat like number.
So it's talking about a serial fraction f.
Yeah, so if the serial fraction f is constant, so that's like which part of the
is a sequential
sequential
is
versus
sequential. Yeah.
If yeah. What's a good way to phrase this? If p% of a program can be parallelized, the max attainable speed up is where f is t serial over t serial plus t parallel. This is a fucking horrible fraction.
There, yeah.
Because in the easy way to write it is if the serial fraction f is constant, the maximum speed up is 1 over f. But that's like the lazy way to do it. But I'm lazy,
Yeah, that's
so
what it says in the slides.
yeah. If the serial fraction f is constant, the maximum attainable speed up is 1 over f. Which makes sense because if like half of your program is if a third of your program is or can be parallelized, or if a third of the program has to run sequentially, you can only get a max speed up of 3. So like
Yeah.
logically it makes a lot of sense. It's just putting it into words is annoying. Right. 6 is explain why these are standard send and receive compose deadlock. Give an example of such a deadlock. Will use shared memory to exchange data lead to a deadlock? Okay. I think I know this one.
Oh yeah. Okay.
So
Because of
if two threads are waiting on each other to send data.
to receive
this will
data.
No, to send data. So waiting on receiving data from each other to send data, this
Yeah,
will cause a deadlock.
because they're both waiting.
Example, thread 1 receive from thread 2, send to thread 2, thread 2, receive from thread 1,
Yeah.
send to thread 1. So this will cause a deadlock.
Yeah.
Shared memory can never cause a deadlock, but it can cause dirty reads. Actually, I don't think we use that term in this course. It can cause reading out of date data, since you don't know if the data has been updated yet. Because like that, there always is data, which is why there is never a deadlock. But
Yeah.
you don't know if the data is the data you want.
And you have also like you had other things as well, right? To sort of avoid deadlocks, like it's kind of non-blocking operations as well.
Yeah. So there's some stuff like yeah. Like actually preventing deadlocks is a whole thing on its own. We had a whole course about it in computer science.
Really?
Yeah, well, it was database processing, but database processing is like 99% of it is just how to not cause deadlocks.
Yeah.
So yeah, if your program can be turned sequentially and it wouldn't break anything, then you can be quite sure that it doesn't deadlock. But yeah, it's actually it's not an easy problem to solve.
No.
Yeah, what is data parallelism in parallel programming?
Next.
It's a good question.
Um,
So I think I know what the owner computes rule is. I'm not entirely sure.
Oh, okay. That's actually literally in the slides somewhere. Like it's
Yeah, I'm
about
sure it is. But, like we can't use the
dividing
slides.
data structures up and giving them to different cores or something, and then each core does the same operation on these on their assigned bits. I think something like that.
data parallelism. Distributed. Okay, so data parallelism is like each thread gets its own data. Yeah, that makes sense. Could have figured that out from the name.
And I do the operation on that.
What does owner computes rule mean? I guess that the thread that owns that bit of data is the one that computes on it. But that I don't.
Owns, yeah, exactly. So it is something to do with dividing the results or something. Let me see.
Data parallelism means every thread gets a shard of the data and works with that data. The owner computes rule is that the owner or the thread that owns that data should do the computations on that data. Is this correct? No idea. But we'll figure it out when we read the slide or when we check the answers.
Yeah.
I do not have a better guess right now. Next. Programming models are based off process threads. What's the difference between a process and a thread? Oh, that one's. I should know that one. A process has its.
Oh yeah.
Has its own memory or heap. And
address.
Address space. Yeah, indeed.
They are independent.
This does cause more overhead. They are independent from each other. And
they are the executable program, right? If you have
ID. They are their own executable programs and run their own instructions. Threads are...
Thread is a lightweight process. I remember like that from the slides.
Yeah, but it's not really true because they're not processes. A process is like something that has its own process ID, which this doesn't. They're all threads are a way for a single process to use multiple cores to do its work. Thread does not have its own address space since it is part of the same process.
Yeah, and they are dependent. For example, they can access the same register, the same variables, something like that.
Yeah, so having its own address or not having its own address space and accessing the same variables and registers is the exact same thing.
Okay.
So yeah, because like if you have its own address space, so own address space means that like if an address space is like the chunk of memory that is yours. So if you have the shared address space, you can address the same data. So if you both have a pointer that you send to each other, you can both see what is at that pointer.
Yeah, okay.
9. I'm gonna move this a little bit. Suppose you want to send the numbers A1, A2, A3 from process A to process B on a distributed memory parallel computer. So real quick, distributed memory, that means that they each have their own bit of memory.
Yeah. And if they want to access other data from other memory, they have to use a connection.
Yeah, interconnects. But in a distributed memory parallel computer, they don't really have that. Well, it depends on how it's done. Using a simple for loop, sending every time, will do the task. Would you advise a program to use solution? Please screen your answer. No. I would not advise them to do this, as this requires the program or the threads to sync up 4 times. Is it 3 times? 3 times. And requires the network overhead 3 times if they use a single send to send the 3 chunks of data at once, since they are all stored sequentially in the array, they only require the network overhead once and to sync once. Does that make sense? Yeah, so like if you use send 4 times, like it's like, okay, send, and the other has to wait to receive, and it's like, okay, do the overhead, is everything received correctly?
Yeah.
Yes, check the buffer, okay, clear. Okay, again, send, go for the network, check the buffer, see if everything's clear, okay, yeah. Do it again, like at some point.
Looks like it takes a lot of time.
Yeah. So
Yeah.
you do have to like wait for the, like you're sending the same 3 bits of data over the network,
Yeah.
or 3 chunks, but there's also the overhead of starting it up, waiting to see if the other process is ready, sending it over, like
Yeah,
that you don't have to do.
How else could you do it? Could you send it in one go, the
Yeah,
3 messages
yeah,
or something?
because they're like A1, A2, A3.
Yeah.
So that's what I said here. They're all stored sequentially in the array, so you can just say send from here to here in the array.
Yeah.
Given a... Okay, my brain really wants to go direct acyclic graph, but I don't think that's it. Age group.
What?
Age group of tasks in a DAG cannot... Have we heard of a DAG before?
I've not, but then I've not looked yet through lecture 7, so I can
don't
quickly see
think-
if that appears there somewhere.
I can have a look in lecture 7. I don't think we've seen it. No, we haven't.
If it's not lecture 7, I think it's maybe material that's not done in this year.
Yeah. I'm just gonna look up parallel processing DAG. Processing of DAG. Yeah, that is a direct acyclic graph. DAG model, DAG execution model of parallel computation. I think this is what they are talking about. Record in a textbook. Are any of these ours? No, essentially. Control F DAG. Dag. Give an input, dynamically create. It is a okay. Just to say, I feel really fucking smart right now. Right. Oh, so
What
this
is
is like
it?
it's a direct acyclic graph. What that practically means is you have. Oh, I'm busting out the paint now, ladies and gentlemen. What that means is you have like task 1, task 2, task 3, task 4, and you can go like, okay, so this one needs to go here. This one is required. Like it's a dependency graph.
Okay. Then that is lecture 6 and 7, or at least lecture 6.
No, I don't think this is lecture 6. So I don't think we've had this. So
We
you
do
can-
have, they do
we do
show
have this.
dependency graphs
yeah, this
in there.
this thing. I
Yeah,
don't think this is
exactly.
called a DAG with us, but yeah,
Oh.
I do think we have had it. Yeah, like just not with this term.
Okay.
Right. So given a directed acyclic graph consisting of a number of tasks, if each group of tasks or each group of tasks in the DAG can or cannot a group of tasks in a DAG.
Even a DAG consisting of a number of tasks. Each group of tasks.
So
Well,
a group of tasks in the DAG. So I think what that means is, I think what they mean with a group of tasks, like one of those circles that I drew, I think that's what they mean with a group of tasks in the DAG. If that is what they mean, then I'm gonna say they have to be executed serially, so they cannot be executed in parallel, because that's how you like group them up, right? Like each chunk of data is here, each node, sequential computation.
okay. Yeah, I'm not sure about this, so yeah.
Yeah, this is my guess as well.
Sounds, yeah, it sounds okay.
Okay, so consider that serialization matrix reversal and calculation. Cache size, numbers or doubles, which loopness leads to a better performance. Oh, I love that. This is always funky. So, we know, I think program 2. So, say that we have like the memory. then practically what you'll have is yada yada yada. So at like x0. So say this is x0. Oh Jesus, that's a bit large.
Oh, okay. I see now. I couldn't see the difference between what the first. It's the change of loop, the in loop and the act.
Yeah.
Maybe
So
in the question, right? It was something about if it's like, for example, in C, like it was more efficient if you would, for example, do the row in the inner loop and the column in the outer loop, and then for fourth one, because it was differently run, you had to swap the loops to make it more efficient. That could
Yeah,
be
so-
something like that.
I'm not entirely sure. I've never paid attention at Fortran. I hate the language. But yeah, like
No,
generally.
I don't know anything about it, but I just remember there was something about it in the lab exercises about changing the inner and the outer loop, that it has an effect on obviously parallelization, but also about some efficiency with it. Like if the program reads it column wise or row wise.
Yeah.
I don't know if that's anything to do with it.
So what is? If you look at my screen. Oh, what the hell? Why is my fucking timer paused? Cringe. Did I press a button? Come on. No. Yeah. Did I press? Okay, I did.
Oh, you're doing a speed run.
Yeah, I'm doing my speed run.
Enjoy.
Yeah, thanks.
Cool.
Yeah, have a nice lunch. Okay. Also, I fucked up like multiple times, and oh, that's why I was crying, because I pressed delete to delete the thing. So this is x2 0 and x2 1. So practically the way that array that matrices are stored in memory is you've
Yeah.
got x, which is an array of pointers which point to more arrays really. So, but after you've indexed once, the second index is just a normal array, right? Because
Yeah.
they call it a matrix, but in reality it's an array of arrays. So
Yeah.
once you've indexed once, you want everything to be in a row, because that's near each other in memory. So if you do this, where you swap the first index every time, then you're looking at this point, then you're looking at this point, then you're looking at a point that's all the way over there. Like it jumps around, right?
Doesn't it matter like how the program stores it? If it does it row or in columns?
So I'm as a computer
Yeah, it does,
programmer,
but in this
generally-
case, it's C. In
Yeah.
this case, it's C, not Fortran. This is a C
yeah.
loop.
yeah,
And C does it in row, right? Like
yeah.
Yeah, like Python. Yeah,
okay.
Like any sane programming language would.
yeah, exactly.
Yeah, because X is an array of arrays, and then in an array
Yeah.
you're near each other in memory. That's not the right button. I need to press this. So yeah, I think the second is faster, because after your first index you want this to change, but not this, because this is near each other in memory. Right. So that's 11, I think.
It's the second one because of reasons.
Yeah. The second one seems to be faster, or will be faster, since since after the first index you have an array which is all close together in memory and won't push other related chunks of data out of the cache, as they are cached together. I hope that makes sort of sense.
Yeah, that makes sense.
Okay.
I agree with the program too.
Yeah. So, and the reason that we say this is we can also say, and the cache is too big, since it's 1500 times 1500 times 8, which is a lot more than 32 kilobytes. This matters because the whole matrix can't be stored in cache, since actually, let me think about this. So it would only really matter So yeah, we would need 8 times 8 times 1500, which is more than this. Yeah. So because a row array, because 8 rows of or because a matrix column of cache blocks cannot be stored in cache. 8 times 8 times 1500 is greater than 32 kilobytes. So I hope this sort of makes sense, the second part.
Yeah. So if it would, like, if say you would have a smaller matrix that could be stored
Yeah.
in the cache
If,
side.
if the entire thing can be stored in cache, I don't think it matters too much.
Okay.
But this, yeah. So it's not like the whole matrix would have to be stored, because with this one, the entire matrix can't be stored in the thing either, right? So I'm just quickly check I'm still recording.
No, no.
I am, lovely. But the thing is, with the other one, you go like down a row and then you go to the second part of the row, like you go to the second row,
Yeah.
and that cannot be stored in that whole thing cannot be stored in matrix. So the moment you go to the second column, not row, you would need to fetch the same data that you just had again, because like I said, a whole column does not fit in memory. I think if a whole column fit in there, at that point you might be the performance might be similar, but because it doesn't right now, it actually matters.
Yeah.
Oh, fuck off. Okay. Parallel program using processors is. This is also so horribly written. Yeah, the workload problem is.
Oh, this is the thing that I find hard.
Yeah. Okay, so if P increases, how much?
This has to
They're
do
asking like
with the
7 questions as well.
T overhead.
Yeah.
Like T overhead over the work or something.
Yeah, but that's just I honestly don't like that way of calculating it. So, if P increases, how fast must N increase to keep the same efficiency? So yeah, practically this workload you can see as the sequential processing time.
Yeah.
So
Which is what we had on the slides, right? We had it's like the P times the parallelization time that it takes
this, yeah.
minus the workload, yeah. And then divide by the workload will give or like from there you can.
Yeah, honestly, I'll learn this by heart before the exam, so I'm gonna cheat. I'm gonna be a little cheat. So yeah, ISO efficiency is overhead over workload, right? That's the main thing I need to know. So
Yeah.
To keep the same efficiency, ISO efficiency needs to stay constant. ISO efficiency is workload over, what did I say, cores? No, workload over, no, it's overhead over workload.
Yeah.
Overhead over workload. Right, let me start writing LaTeX, because there's a reason I'm doing this in Overleaf. So DO is, overhead is B C dot TB minus W.
Yeah.
DO is B C dot, and the overhead was frac, and this was B, and this is n to the power 2.5 plus n, I think it was. Yeah, over p plus p times n to the c dot n to the power 1/2, a half, a half, a half.
So
And then
there's a
minus,
couple of questions in there. So once we computed this, like the TO over W, it's like in order if P increases, how fast must N increase in order to keep the same efficiency? So I guess it's comparing the P with the N in that equation.
mhm.
And then it says if the problem size N is increased, we keep the computing time constant by using more processors.
P, c dot. Okay, let me recompile. Oh, of course, let me just fucking add line endings. So I can actually read it? Oh, I haven't closed the bracket. Oopsie. And, oh, the backslash needs to go. There we go. So these two terms cancel out, the n to the power 2.5. So then we get, so the overhead is n plus p squared times n to the power half, so square root of n. ISO efficiency is T frac T O W. So we know that TO is this whole
N
thing,
plus. Yeah.
and W is n to the power 2.5. So let me have a look at that. Yeah, so we can lower this by a half, but I don't think this. Yeah, this is just ISO efficiency is no fraction anymore, n to the power minus 1.5 plus n to the power minus 2. So yeah, this needs to stay constant.
Yeah.
If my math is correct. How fast must n increase to... Oh god, I always hate questions like this.
Can't read it properly. Wait, let me just go on the.
I'm just checking my math real quick.
P increases. How much? How must N increase? Gen-
So, the interesting part, how fast must n increase in order to give the same efficiency?
So I can't see the. Wait, make the screen bigger, I guess.
So no, that's just Discord being bad. Let me, I can either reshare my screen or change the resolution.
What do you have? N minus 1.5? Yeah, thanks. I can see.
Yeah. So 1 over n to the power 1.5 plus p squared over n squared, practically. So if this
we're just comparing P with N now, right? If we're
Yeah.
keeping the efficiency constant. So we could just maybe put 1 to one side and then P to the other side. So we have a nice comparison. Like we see how much N needs to increase if P increases.
Yeah, so we can do that. So that would give us minus n to the power 1.5 equals b squared. Actually, so what I'm no, never mind. B squared c dot n to the power minus 2. And if we multiply that out, we get n to the power, or minus n to the power a half is b to the power, or b squared.
So
No, actually, am I wrong? This needs to be a minus, and then I'm right. Yeah.
minus n to the power to the half to a half, right? Or if we take the n to the minus 1.5 to the other side, that becomes minus n to the minus 1.5. And then if we divide it by, so we can do maybe times n to the
n
power
squared,
2.
yeah, and n squared.
So then that is minus n.5 with power half.
Yeah, minus n to the power half, that's what I have as well. Let me recompile so you can see it.
Yeah.
Let me,
I can see.
yeah.
But so then and the question is, if p increases, how quick must n increase? So then that's given there to the minus with 5.
Yeah, so practically, the annoying part is that, yeah, I feel like this doesn't work, because like ISO efficiency needs to stay constant, so it's more like constant minus something, and then you divide the constant as well, which is weird. I don't know, I don't like the math here. I can just be, yeah, we'll just keep it at this. So if you want this to stay constant, if b increases, n is gonna have to increase by, or it has to increase by n to the 4. So with if b increases by factor a, n has to increase by a factor n to the, or a to the 4, which I don't think is correct, but I think looking at the answer will definitely teach us something.
Yeah.
If the problem says n is increased, can we keep the computing time constant by adding more processors? Right now, I'm also, let me recompile this.
So maybe we would just have to look at the TP, or
yeah, I think that's the.
now it's asking to keep that constant, right?
If the program size n is increased, can we keep computing time constant? So, if we look at.
And now we just look at that formula of TP, I think.
Yeah. So
And now if we say we keep TP constant,
yeah.
just like we did with efficiency before.
So if process n is increased. So say program. So if n is increased, we're gonna need to increase p to counteract that.
Yeah.
However, that will just blow up this part. So I don't think we can. Because one side gets smaller as p increases and the other side gets bigger.
Yeah, I was looking at it wrong, like because it's written like on one line like that.
Yeah, because say n becomes huge, p has to become huge to cancel that out, but this part would blow up then.
So if n gets bigger, I see what you mean.
Yeah, because say n is 1, then yeah, then we can keep it down, but say, yeah, because you can't just keep throwing more cores at it, because eventually throwing more cores in it will just diminish this part and make this part bigger than this part.
Yeah.
So yeah, because you can't because there is a limit at how many cores is useful. I think that n outgrows that.
Yeah,
So-
I think it at some point it doesn't have an effect anymore.
Yeah,
I think.
eventually, the if you give more cores to it, or the second term will be bigger than the first term. The second term of t underscore p will be bigger than the first term. I hope that makes sense.
And in that first term, it's like n to the, what does it say? N to the power 2.5.
2.5. Yeah.
And a half. So that's that
So
makes
you need
much
to grow.
more.
Yeah, you need to grow p very quickly to catch up to that. If that makes sense. This will be. Why does it not recognize? Oh, because this is not a fucking computation. Sure. Yeah, there we go. Okay. If the process can we keep the computing time constant? No. What happens to parallel efficiency in that case? It goes down, right? Because adding more cores doesn't give it better performance. It goes
In those graphs as well.
down since adding more cores doesn't mean better performance. So this is what did they call it? Subliminal, suboptimal? Yeah, sublinear speed up. Whoa, crazy fancy terms. Right, let me close this. Okay, so what are flow dependency, anti-dependency, and output dependency? Is it often possible to avoid or remove through restructuring a program? Yeah. So flow dependency. I think flow dependency means that to do your calculations, or every calculation requires the previous one to be done.
Yeah.
Anti-dependency, I think, requires for every calculation the next one to not be done. Not sure about that one.
The output dependency is that you have two things that are outputting the same variable or something. Like,
Yeah.
Yes, I'm very
down.
so
Okay. So flow dependency. Wait, let me go back to.
flow dependency.
When the output of the one iteration is the input of the other.
Yeah, true.
So we can write that one down. Output dependency when the output of one iteration is the input of the other.
Yeah, output in one is the input for the other. Then anti-dependency.
The dependency is what you get when you have a loop and you parallelize it, and the last bit of one loop overrides the other bit. Or in other words, you have, for instance, have an R2, and
it's
one.
the next step or something.
Yeah,
Yeah.
it was a race. What was it called again? When you have a race problem.
Yeah.
Shuttle race.
Yeah.
That's what you get with anti-dependency.
Yeah, one computation can't be, or when a later computation can't be done before an earlier computation. And flow dependency is when a what's to say in my head the same thing. When a later computation.
Which one are you at now?
Flow and anti-dependency.
When I write
Flow and anti.
Yeah.
No, No, flow means one computation is needed before the other, and anti-dependency, they overwrite the same data. So they can. Or
But
is
is
that
it
wrong?
not that it's
Oh,
it's
sorry, it's
used,
wrong what I said.
something is used, the variable is used to compute something, make and get an output, and then that same variable that's used is then overwritten in the next
Yeah.
step or something.
Yeah. So anti-dependency, if you do it wrong, something's overwritten, you use the wrong thing. Flow dependency, you simply cannot computate the next step.
Yeah. That's a nice way of putting it.
But flow dependency, you will get an error. Anti-dependency, you will get a wrong result. But not an error.
Yeah. Otherwise, out of date data is used. I feel like flow dependency doesn't require to give you an error. You might just be reading bogus data.
Oh yeah, that's true. It could also be reading something else that's there.
Yeah. Yeah. Keep it at this for now. 14. What is the data locality ratio? So I know that I don't know the exact numbers. I know that A plus B has a very high data locality, since to compute one term, you only have or you can like use one term of the other, so you don't have to like constantly jump around the matrix.
Mm-hmm.
And for the other one, you do. So I can for sure tell you that the plus B has a better parallel efficiency. But if you want the exact ratio, I'm gonna have to look into the slides.
I don't think the A plus B has better, because parallel efficiency depends on the number of jobs also, right? And A plus B is just n number of instructions, but A times B is much bigger.
Yeah, but A plus B, like if you have
You have small number of jobs, it's not efficient to parallelize it.
Well, I think that even with A plus B, if you have like, because every single term, like if you have a 3x3 matrix, you can put 9 cores on that, and it'll be 9 times as fast. Because you can completely and utterly parallelize that. At the same time, A star B, you can also give every term its own thing, but it will have to.
Isn't that like you have
honest,
copies of the? You have this like similar copies of each other. Like you need to spread out more data for A times B to different cores compared to A plus B. Isn't that the idea?
I'm just gonna look at the slides. This is lecture 1, should be lecture 6, I guess. Let's talk about matrices. Control F, data locality ratio. Okay, apparently it's on the slides. Data locality ratio of operation parallel computing. Yeah, I don't think we got taught this. But yeah, so I think that if you give like a whole column or a whole row to a whole row of A and B to a processor here, it will need to cache very little because the data is very local. Well, for A times B, the data is not local at all. Like it can be scattered everywhere across the entire fucking memory space. So, while I think A plus B, because indeed parallel efficiency I can't really say for sure because I would have to like calculate the speed up and everything, and I don't know how to do that. But the data locality of A plus B is higher, I think.
Mhm.
I got no idea with this one. Just a bit. Did we have anything
Nope,
about
we
data
didn't.
locality?
Okay. 15. What is a multi-stage switching network? I guess that instead multi-stage switching.
Like an example is the Omega network from that, right? Like a
Yeah,
dynamic.
it's like you have multiple rows of switches.
Yeah.
And compared to a crossbar network, I'm guessing a crossbar is like a static network where you have like one layer in the middle, I guess.
Is a crossbar static or dynamic?
I'm not even sure, to be honest. I know for sure that the disadvantages of an Omega
Dynamic
network.
network, what I remember, but maybe I'm wrong.
Disadvantage of an... Is it Omega network? Yeah, Omega network. Of an Omega network is...
What are the advantages of an
is
Omega
that-
network? Oh yeah, we mentioned this collision thing, right?
Yeah,
Like
yeah, you might get collisions since only a part of the mappings can be done in parallel. Advantage is that you need fewer links.
so that has an effect on the cost.
Yeah, which is cheaper. Although you do need smarter switches. No, actually that's not true. Yeah, which is cheaper. I'm going to change it to which gives lower cost. Because it's not about money. Yeah, and then they ask what is a multi-stage switching network. That's going to be a network where data has to go through multiple
My God, I just read
switches.
question 16 and I didn't understand a single word of the question.
Question.
The next question, question 16, I just read it and I didn't understand a single word of the question.
It's from numerical, I think.
Yeah.
Yeah, I think that's lecture 7 as well. Like, so I've not really looked at that. Yeah.
Oh, this is gonna be a funny exam.
Yeah, but don't forget, this is from like 5 years ago, so this is not at all indicative of what our exam is going to look like.
Yeah.
Numerical.
Hopefully.
So we know that a Poisson equation is kind of that wave equation that we did for the numerical exercises. Don't know
Yeah.
exactly what it is, but it's like I think Poisson equation is that f is negative divergence of u. I believe that's the Poisson equation. Discretized with a 5-point central difference tensor. So that central difference, I think, has something to do with the
The discretization.
yeah, it's a way to discretize. Yeah, well, which it says here. What's the purpose of applying red-black order? I remember this. Holy shit. So this was in lecture 7. This was in lecture 7. Red-black ordering in the parallelization of Gauss-Trial iteration for this problem. So red-black ordering, if my memory doesn't fail me, is like, and I know for sure that this is not exactly what it is, but it is sort of what it is. which is always very very nice to hear when you're fucking.
I'll
doing an
open
exam.
lecture 7 just in case,
Yeah.
Jelle. But
So-
go on.
What this means is like you have this entire like grid, and what you do is first you do. Oh god, they're not completely connected or whatever. So this one is red, 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 red. Like you have this whole fucking row
The checkers
system.
board.
Yeah, the checkerboard. And first you do this task, then these two, then these three, then these four, then these five. So that like
Wait, what is this?
this
that
is the
you're explaining?
red black ordering of tasks.
Ah,
So
okay.
you have like this whole list of tasks, and the dependency kind of goes. So this task depends on this one. This task depends on both these two. This task depends on this
Ah,
one
the
and this
type
one.
sensitive
So
thing.
yeah.
Yeah.
So you compute each row of dependencies first, so that you're always ready to compute the next one. So the answer will probably be wrong, but in the right spirit.
If you get half of it, is good.
Yeah, it's better than.
Yeah.
Better than my answer, that's for sure.
So since so yeah, you use red black ordering to divide the tasks such that the requirements for one computation are done before the other, or before the next one, or before that computation. This makes it so that the minimum or the maximum amount of tasks running in parallel are so say this is n tasks. One edge is square root of n. So the diagonal will be square root of 2n. Yeah.
What?
Yeah, I'll explain. Probably I'm wrong, but
Is my audio still bad, Guy? Just read your message.
I think it's
Bad.
No, it's good.
Hamra asked if her audio was bad.
Oh, okay. I thought you said like my audio is bad.
No.
Yeah, so
No.
in here, say you have n tasks, then one edge of this like block is square root of n, right? So the like diagonal line here would be by Pythagoras, which is the most weird thing to use here. It would be square root of 2n. Because it's 2n squared.
No, that's not
true.
2. It's n.
No.
It's
Count them.
It's the same as it's n. I learned this from Tim.
Yeah.
It's n. It's not Pythagoras. It's not a line. It's just numbers. The main diagonal has the same number of elements as the row and on a square matrix as the row.
Oh, yeah, you're right.
Oh yeah.
So it's not square root 2n, it's square root n for n total tasks.
Well, there's n squared total tasks, I think,
there's
right?
n
It's
squared
every
total. Yeah.
the matrix has n squared elements, and so you still would do the square root of the amount of tasks, but that's the square root of n squared.
Yeah. So yeah, the maximum is n for, and the thing is, I don't know what n is. Is it like the size of the matrix? I don't fucking know. So I'm just gonna say n tasks because I do not know what n is.
There's 5. The parallelization is 5, I think. No.
Well, it's a 5-point centers difference stencil. So
No, maybe I'm talking bullshit.
Yeah, so they don't ask for a number. They say, what is the purpose of applying red black ordering? Your red black ordering to divide the tasks as the requirements of computation are done before the computation. Make sure the maximum parallel is equal to n for n tasks. So yeah, so we are doing it because this does it in a way that the requirements are done before it, and that the maximum amount of tasks are running at the same time, practically.
Yep.
Okay. Is it the exact right answer? No. Is it something that's close enough? Yeah. Fucking sure. No. Alright.
Yeah.
Then I'm gonna
What
pause the
if we
timer,
completely wrong
plot
now?
13, and then we go to the answers. Because I think that was the entire exam.
Yep.
And then we pray that we got like a few of them right. So then we just split this up and go shabam, shabam. And then hide source text. There should be a way to do this. No, can I not hide my source text? Oh well. Okay. Yeah. So so they're talking about the they're seeing it in a different way. So they have the interconnect network. So the way that they talk to each other, the way that each node in itself works, and the way and how the memory is shared. I don't know if I would get points for this. Because I think like I actually, yeah.
In memory is in there.
Yeah. So the
No?
the interconnect network is in there. That's the link. The node is in there. That's this.
The
It's just that
architecture
I was
part.
talking about switches, and they're talking about the memory organization.
Oh yeah, Isabel said memory.
The interconnection network, maybe you get
Yeah, I
point.
think because my interconnection network is link because that's like the network.
Yeah, exactly. And that's
so,
the static versus dynamic network.
The problem is each count for 1 point, so I probably get 2/3 of a point for that.
Yeah.
So I'm gonna be lazy and just open Word. So I keep
Hey,
track of
well
my
done
shit.
you.
1. No, well done us. 2/3. What are the main properties?
Let's be generous with the points.
Bit of confidence booster.
That's a very weird fucking thing to say. What are the main properties? Diameter and the bisection bandwidth. That's not main properties, right? It's not like that's.
The performance metrics. But we did say, yeah, I think we named pretty much everything that was in the slide.
These are in here.
Yeah.
Yeah. So I named diameter and I named bisection bandwidth.
Yeah.
What's the main difference
Why
between
is it just
subject
those two?
not discussed, so not part of the exam? I fucking 3 dash.
Well, that makes sense. I was like,
Yeah.
I've not heard of that.
Describe single structure. Bro, fucking, they didn't even. This is not describe the meaning.
Single program, multiple data, but that was we couldn't even find that in the slides or the book.
Yeah, I'm giving us 1 point. Fuck that.
This stuff?
What the fuck?
Are we talking about 3 or 4?
4.
And I mean,
For-
here
but-
it's also
SPMD wasn't in the
describe
slides, according
meaning,
to
right?
Man.
I don't think so, no.
No, yeah. So they.
1 and 2 was SP, not.
Yeah. We have 1 and 2.
Yeah.
Yeah. So the fun is, or the weirdest thing is that like. Yeah, the maximum speed up is bounded by 1/f. Yeah, so we had this correct. Abdel loss is given a serial fraction of program maximum speed up is bounded by thing. So we had this correct. They gave a more detailed explanation.
Like that. It was literally in the slides
Yes.
like that.
Send and receive are blocking. We'll wait for each other until the message has been transferred. An example is that each other the message are larger than the internal buffer. Both persons will wait the other. So we didn't do this, or we didn't talk about the buffer.
We did say that they were waiting for each other, which is in a way they're blocking, right?
Yeah, okay, that's true. Although we didn't say about the internal buffer.
No.
But
I don't really understand, to be honest. So what does it say? What is that part?
So apparently, if there's an internal buffer, it can just write it in the internal buffer, and then when the other one gets there, it just reads it.
Okay.
But it can only be done if I'm making this shit up, by the way. I don't know, but this makes sense, right?
Maybe I'll make a note for myself. Read up about internal buffer.
Yeah. I mean, that's what these sessions are for, right? They teach you what you know and what you don't
Yeah.
know. So yeah, the internal buffer is just like it writes it in there, and if it's too big for the internal buffer, it needs to have the other one say, okay, I'm done with this part. You can delete it, and you can write some more. Yeah, and otherwise, if that isn't there, if the other program isn't there to say that, then and it's too big, then you have to wait.
I was wondering as well something, maybe you know, Jelle, because some of these concepts are just completely new for me. So I'm just reading stuff from the book. There was something about synchronized and asynchronized method of doing these processes. And if you do, for example, synchronized, will you have then lesser use or it will be less likely for there to be deadlocks? Because then I guess one will have started already before the other one has finished, right? I think something
So
like that.
the way I think about it, or the way I think that means is if it's synchronized. So that I think what that means is everything has to finish their instruction before the next one begins. Then
But that's not synchronized, I think, right? Or
asynchronous means they can run independent. At least that is how I feel like it is. So, and synchronous would
Okay.
then mean that they cannot run independent and they need to wait every single instruction. So they need to synchronize after every instruction. I think. I haven't read the book, so I don't know what synchronous and asynchronous means here. But if that is what it means, then
well,
synchronous
I read it and
always
I found it
deadlocks.
really difficult to like sort of picture it because I thought exactly what you're saying. Like, I was like, oh, synchronize that they can run independently of each other.
No,
But
no,
then
no.
the way the book
Asynchronous
said
is
it,
independent.
yeah, and
Synchronous
then
isn't.
synchronized is that it overlaps in a way, right? A little bit.
Well, so like I said, I don't know what it exactly is to mean, but if you are talking in the way of, so in the programming terms, asynchronous and synchronous, or synchronized and asynchronized, then asynchronous can run independently from each other. They don't need to like talk to each other. They can just move independently. While synchronous waits for each other after. Yeah, they wait for each other. So synchronous here
Okay.
would be after every message wait for each other, or after instruction wait for each other, and at that point you would either always have a deadlock or never have a deadlock. While asynchronous
Okay.
creates highs and bugs and race conditions, which mean that sometimes you have a deadlock, sometimes you don't.
Okay.
Did you want to say something?
Me?
Yeah.
No, that makes sense what
Okay.
you're saying.
Okay, good. What is data parallelism? The same operator must be applied to different sets of a large structure. Data approaches partition of the same parts each parts to a processor. We said that part.
Yeah.
Yeah. Okay. So I think this part we got because we said every thread gets a shard on the data and works with that data. They said it a bit better, but whatever. Only computes assign each part of the result to a processor in a parallel. Each processor computes the part of the result assigned to them. Not exactly what I said. So I said on the input, and they're talking with output here.
Yeah,
So I
they're
think I
talking
would get
about
like
the
a half point
result.
here because I got
Yeah.
one correct, one wrong.
This is the only question I could answer. The first part. What is data parallelism? This one is good. I hope he asks again.
Yeah, I hope so too. Okay, what is the different process have its own address space? Yeah, local space process local space not directly with other processors. Yep. Threads are a common address space. Yeah, so the others can access it too. It's a lightweight process because no data needs to be copied when creating a thread. Yeah, I didn't say that part. Do we care? Do we think that they are going to deduct points for not saying this? I don't think they are.
No,
We
I
did
don't think so.
discuss
Yeah.
this.
But I think if you put this, he's gonna like because he says
I mean, the
is
lightweight
lightweight.
process is all over the slides, like in all the comparisons he does. He puts down lightweight process.
Yeah.
But-
I mean, we did say that.
If you explain it in a slightly different way, then I think that doesn't matter.
Yeah, no, I didn't say lightweight process, but at the same time, explain what the difference is. And I explained the difference, namely the address space. This is just a consequence of that. So this is not what they're asking for, really.
No.
Or well, they just say in contrast. So yeah, I'm missing a part of this. I think I would still get the full point here. Yeah, communication time. Yeah, they're going more in depth, but indeed, like I said, the setup time, which I call network time here, you would need to do all that 3 times. Although I did say sync, and not really. You don't really. The sending doesn't need syncing if you have an internal buffer, which I forgot about during this exam.
Well, we did say by sending a message of 3 numbers as one message. I remember we did say that.
Yeah. No, so the only thing that I think is wrong here is that I said that we need to sync up 3 times, and the network overhead 3 times. But no, it's just the setup overhead 3 times, not the syncing. I still think that I would get like at least half a point for this, because I got the essence.
For sure.
Yeah.
Yeah, I think so.
We are generous with point giving.
Yeah,
so.
yeah.
I think this guy looks like the type of guy who's trying to fail people, to be honest.
Really? I don't think
I
so.
don't know.
I think he's like, yeah, that's
Well,
got
when you're
some-
asking questions about the report, he's always I said I don't think he's gonna fail people. I think he really.
Okay, that's what you mean. Yeah, no, I
If you
agree.
ask questions about the report, he's like, yeah, that's good, and then you look someone else's answer, much better. Yours was already good. So
So
I don't
I
think
mean,
he's here.
like,
Fuck us.
let's just assume that he's generous, because if we grade ourselves on like what
Yeah,
he isn't,
yeah.
that just sucks.
Yeah.
Yeah. Again, here we had the part about data as read to the cache in groups, so and the fact that it cannot be stored in memory.
Yeah.
So we had those 2 parts. If the data is stored in a row structure C, program 2, yada yada. Okay, sure. I should have said, well, it's in C, but like this is a C loop. Fuck you.
Oh, but we did say that because I remember Guy was like, "This is written in C."
Yeah, so I didn't write it down, but we
Yeah,
did
yeah.
say it. I'm giving us the point.
Yeah,
here
we
then.
said it.
12.
Is that it?
Execution time. Yeah, so it's
When the row major structure, that's what I meant when I was saying like one does it in row, one does it in column, blah blah blah. Yeah.
n should be increased proportional to p when p doubles, and should be increased 2 times. Yeah, so we were wrong here. I guess then, yeah, we should have just kept it at this and just ignored the n part.
Oh, so wait, so yeah, this is a bit vague. So what does it do? TSO, what did we have?
So we kind of did some stuff that isn't really allowed by math, where we set this iso-efficient part to be 0 and then continued from there,
Yeah.
but it needs to be
Yeah,
constant.
yeah.
So, but otherwise our calculations wouldn't make sense. I guess we just ignore every part that doesn't have p in it and just look at that. Because if you increase p by a factor of 2 and increase n by a factor of 2, then this is also going to increase. So it doesn't stay constant. But I guess that's not what they're asking. I don't know, it's unclear. I guess just only look at the stuff that has p in it.
Unclear.
So yeah, we did that wrong. If the program size n is increased, can we keep it? If p is relatively small, can be kept constant. In such a case, can be kept constant. Yeah, so I think we get 1 point here because.
Yeah, but can I ask something about when the efficiency is constant? I think the reason why I said, oh, we can just bring one to the other side is just to compare the two, like what p does and what n does.
Yeah, but like, yeah, I don't think you could do that. Like, you can only bring it to the other side. So if we do it properly, it would be iso efficiency minus iso efficiency minus n and a half, and then it's iso efficiency over n squared, and then like that doesn't really teach us much. So I guess you would just have to look at this part and just only look at the parts with p in it. That's my guess, anyways.
Okay.
But the other part, I think we said if eventually, if you add cores to it, TP will be bigger than the first term, or the second term will be bigger than the first term. And here they say if p is small, it can be kept constant. So I think we're saying the same thing.
If p is small and increases but time can be kept constant by using more processes. Okay. If p is small.
Yeah. So and we're saying they're saying if p is small, it will stay the same, and we are saying if p is big, it will go up. So I think we're saying the same thing, really.
Okay.
Refer to fuck you, man. That's lazy.
Look at the slides.
That is lazy. Output dependency, the loop dependence can be. We completely forgot about this. Sorry. Yeah, can be avoided by copying the array to a temporal array. Yeah, I knew this. Like you just copy stuff over so that you can so that each thread gets its own copy to fuck with.
Output. Okay. Oh, we forgot to do that part.
Yeah, that's on me.
Okay.
Yeah. I guess we'll look at the slides and see. Yeah, I didn't write it down because I didn't find it important, but that's on me. Let's see, so I need to go to content. Lecture 3, PDF. Bro, it's not even lecture 3.
No, it's in lecture 2.
We're being scammed. Lecture 2. Lecture 2. I think it might. Oh, yeah, there it is.
Yeah,
So,
that's it.
flow dependency was previous output needed as input. Yeah, okay. So, flow dependency has to be done before a later one. Yeah, so these are both correct, but it's not giving us the core of the idea. But that's because, honestly, you guys were right here, and I just wrote it down wrong. Yeah, previous output needed as input. Yeah, the value as input overwritten. Yeah, and
Me,
overwrite.
this helps, this visualization. I always try and remember it like this.
Yeah,
So, like
I'm just gonna like study this honestly. For now, I think on this one we get like. So you guys would get 1 point out of 2. I would get 0 out of 2. Ooh. So 13 is 1 out of 2 for now. 14. What's the data locality? Okay, equal to computing time between two consecutive communications over communication time. No idea. Let each processor produce and look at it.
I really feel this is not in any of the.
Yeah, I'm just gonna say this is not talked about in the slides.
Yeah.
15 multi-stage networks is several stage switching. Yeah, so here I said a multi-stage network is yeah, data has to go through multiple switches to get to the other node. Yeah, several switches. Crossbus are more powerful. Fast to P2P connection can be realized provided all pairs are disjunct. High cost. It should be P squared. Slower. P stages to have 1. So I think crossbar networks, just everything is connected.
Yeah. Yeah.
Yeah, so we said disadvantage that you might get collisions and you need fewer links, which is lower cost. So lower cost we said, collisions we said, we didn't say the Omega network. So I feel like we get 2/3 of the points here. Well, so we get 2/3 plus 1 point here because we had the multi network correct. So I think we get like 5/6 of the points here. Right. Consider the numerical. Holy shit! Can I just skip that one? This is so much text. Calculation update also uses newly calculated update values for current iteration. The value xi uses 2 neighbor values from the previous iteration to current iteration for the parallel implementation. You cannot simply partition 2 registers of each processor. Using practical, it's split into half steps, one for all the red points, one for all the black points. Switch dependency is decoupled. The reps are updated on the values neighboring black points belong to the previous iteration needed. Therefore, modified data dependency with the red ones could be parallelized. I don't think I touched on any of this. I don't think I understand enough that I could say I've touched on any of this. I'm going to give myself 0.
Either. I still have to look at lecture 7 for sure, and just.
I'm just going to hope that it doesn't come up often in the mail. Right. So we have 0.666 plus 1 plus 1 plus 1 plus. We definitely passed. I can tell you that much. Question 1, question 2, question 4, question 5, question 6, question 7, question 8, question 9, question 11, question 12, question 13, question 15. So this is 5/6. No. It's 10/12.
No, that's the same thing.
Yeah, but oh, you're right. It's 10/6. You're right. Good
Yeah.
catch. 1 plus, and the visor should be 1 plus 1 plus 1 plus 1. So 1, 2, 4, 5, 6, 7, 8, 9, 11, 12, 13, 15, 16. Right, let's throw this in Google because Google is my calculator. I hope it's gonna fucking understand this. Hey, 11 and a third, lovely. And this is over 17. 11 and a third over 17 is 6.6. That'd be a pass.
Nice. So if we have all the slides, we can pass. That's great to know.
Yeah. And if we're like having 4 brains together, you know,
Mm.
yeah. Is that correct? So we lost quite a few points on the multiple points question. So 1, 2, 3, 4. We lost 4 points there. I kind of feel, is that right? Hold up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9. 10, 11 and a half. Yeah. Yeah, I feel like
Do you have any plans of solving the other 2 exams? I don't mean now, but at some point.
honestly, I would do now.
Yeah, let's do now. Let's just try, because at the same time we can
Yeah, like,
also
we're all here now,
look at
anyways.
slides and
All right.
also
I am gonna tell my D&D
new
group that I
plan.
won't be here today because we've got D&D at 2.
Oh no.
I mean,
Are you
let's
the
be real.
DM?
Fucking school goes first,
Yeah,
and the
that's a
exam
good
is
option.
tomorrow. So
Tomorrow. Yeah. Yeah. Okay. Can you share your answers also from this one? The
my DM is not home for the weekend. Lovely. Let me just hide that.
The answers for this one are on you mean this
yeah, I know,
particular?
but I also want the answers that he wrote because the way that the teacher writes his answers, I don't get it so much sometimes.
I
The
can
way
send
that
them
the
to
Yelle
you,
writes, I do.
but
Yeah.
so I can't promise that any of these are correct. But
No,
if you
it's
want
good.
just
It's
the
good.
way I've written them,
Yeah.
I'll
For the other
I'll
2
I'll put
exams
this in
also.
a quick latex
What is
document.
nice, Jelle, is that because you are from computer science, so I feel like you have more of a in-depth knowledge behind this kind of thing. Whereas I'm literally just, getting my knowledge
Licking
directly from
rocks.
the teacher's slides. And I'm just like, yeah, I don't know really what it means, but I'll just write this down.
Yeah, I do like. I definitely like chose this study because I have a. By the way, for the people watching, because I think I'm still recording, I am lovely.
Yeah.
I thrown the latex file in the general voice chat message. So if you look here, it is in
Nice.
here. Lovely.
Wow.
So let me just check if I'm sharing the right screen. That should have been. I should have checked that ages ago. I am. Okay. So what I'll do then is I'll
Already
make
missed.
a new project, call it Parallel 2, or Parallel Exam 2, create. Actually, how does it sound to have a lunch break? Because I haven't had lunch and I'm starving before we start the second exam.
Sure.
Good. We could maybe start, but when do you wanna? How long
Honestly,
do you wanna lunch for?
my plan was to be back at past.
Yeah.
Okay, so then I'll
Okay. 1:30.
yeah, I'll end the recording here, and then I'll start the recording again once we begin again. But please do remind me to start the recording.
I'll remember.
Okay.
Well,
Well, then this is part 1. This should probably be 2 YouTube videos. I don't care. So I'll stop the recording, and there's probably a link to part 2 in the description. Yada yada.